Okay, we need to outline a laboratory procedure for producing and observing atomic spectra. The IB say that students should be able to outline procedures for both emission and absorption spectra, but the details of the spectrometer, the device that looks at the spectra, are not required. So we have a hot black body. A hot black body is able to emit radiation in all parts of the spectrum. And there we have a continuous spectrum going from violet to red. In another line of sight we have a cloud of cooler gas. Now this cooler gas is going to absorb some of the radiation, with some lines missing because they've been absorbed by the chemicals in the gas. So this is the absorption line spectrum. Now the chemical in the gas which has absorbed these lines is basically then going to re-emit these lines in all directions. So we view the gas from another direction, and then those lines that have been absorbed from the continuous spectrum are now going to be emitted, and we will just get only those emission lines in another spectrum. So this is called an emission line spectrum. Notice that the lines that are missing from the absorption line spectrum are exactly the lines that you will get in the emission line spectrum. Now, why do we get this? Here is an interesting demo to show how energy is quantized in atoms, and we have this demo here that I will try to show you. We're interested in this part here. So we have to add a line to a spectrum. All the light will come in this atom, and some energy will be absorbed, and we'll take it from the bottom level up to here. So, but only there. It can't go a little bit beyond and can't go there. There are only certain levels, so there are only certain allowed energy differences, energy transitions within the atom. What is this energy? What this photon of energy is equal to HF will basically be between E1 and E2. So it's going to be between 0.54 and negative 0.54 and negative 2.18, and that will give an energy which corresponds to a wavelength of 121.6 nanometers. Now this is a very big jump in energy, and this line is going to be so far off the UV scale that we're not going to be able to see it here. So if I try to add the line to the spectrum, it's not going to show it. So let's try the next series, which is going from the E2 line. Let's go from there to there. The energy difference between the N2 and N3 is going to be 0.54 minus 0.24. What is this energy difference? Well, this is going to correspond to an energy which will give rise to a line which is the 656.8 nanometers, which is in the red part of the spectrum. If we try to add the line to the spectrum, that's where it goes. Let's try another transition from the n is equal to 2 line to n equal 4 line, and we have another energy difference from E2 to E4, gives a short wavelength which is in the blue part of the spectrum, 486 nanometers, and we'll add that line to the spectrum. Let's try another line which goes from there to N2 to N4 to N5. Yes, from E2 to E5, that gives a line of 434. Well, this goes from 400, so that line is going to be there. So this is the third line. I wonder if there's a line before 400. Let's see if we can take the other line here. So it's from N2 to N6. Maybe there. Aha, that's just over 400, so that will also be added to the line spectrum. So we see we have this line spectrum which corresponds to this series, which is basically all going N6, N2, N5 to N2, N3, and down to N2. I could try another line which is higher, and this goes to 389, which is lower than this. I tried to add this to the spectrum, it doesn't accept it because this is not part of the visible spectrum. Okay, so you need to be able to calculate wavelengths or spectral lines from the energy level differences and vice versa. So let's look at an example of this. We have an electron goes from the n is equal to 2 line to the n is equal to 1. What is the energy difference? From 340 to 13.6. First of all, we must calculate the energy difference. This is in electron volts, by the way, so we have to multiply by 1.6 times 10 to the minus 19. Okay, and we end up with 10.2 electron volts. Convert that into joules, and from that we can work out E is equal to HF and find out the frequency of the light, and therefore we can work out the wavelength. So this gives a wavelength of 1.22 times 10 to the negative 7, which is well into the violet part of the spectrum.